Right now, as you watch this video, you are experiencing one of the most profound mysteries in all of physics, the bizarre weakness of gravity compared to the other fundamental forces. The electromagnetic force that keeps electrons bound to atomic nuclei is approximately YY times stronger than the gravitational force that holds planets in orbit around stars. This number, 1040, represents a difference so vast that it challenges our understanding of why the universe works the way it does and has driven physicists to propose revolutionary theories about extra dimensions, parallel universes, and the fundamental nature of reality itself. To grasp the magnitude of this difference, imagine if the electromagnetic force were represented by the Empire State Building. On this scale, gravity would be smaller than a single atom. In fact, it would be smaller than the nucleus of an atom. This extraordinary hierarchy of force strengths is so extreme that it seems almost impossible for both forces to emerge from the same underlying physics, yet they apparently do. The implications of gravity's weakness extend far beyond academic physics. If gravity were even slightly stronger relative to electromagnetism, say only 1030 times weaker instead of YY times weaker, stars would burn through their nuclear fuel in thousands of years instead of billions, making the long-term evolution of complexity and life impossible. If gravity were much weaker than it is, matter would never have clumped together to form galaxies, stars, and planets in the first place. This creates what physicists call the hierarchy problem, one of the most important unsolved puzzles in theoretical physics. Why are the fundamental forces so different in strength? Why does gravity appear to be singled out as extraordinarily weak when the other three forces, electromagnetic, weak nuclear, and strong nuclear, are all roughly comparable to each other in strength? Dr. Lisa Randall from Harvard University, who has pioneered research into extra dimensions and hierarchy problems, explains the profound nature of this mystery. The weakness of gravity compared to other forces is so extreme that it suggests we're missing something fundamental about how the universe works. Understanding this hierarchy might be the key to discovering new dimensions of space, new particles, or even new principles of physics. The mathematical description of force strengths involves fundamental constants that appear to be fine-tuned for the existence of complex structures in the universe. The gravitational constant g, the electric charge, E, and other fundamental parameters seem to be precisely calibrated to allow the formation of atoms, molecules, stars, and ultimately life itself. But the hierarchy problem goes deeper than just comparing numbers. It challenges our understanding of how fundamental forces might be unified at the deepest level. If all forces emerge from a single, more fundamental interaction, as many physicists believe they must, then why do they exhibit such dramatically different strengths in the low-energy world we observe? String theory offers one potential explanation by proposing that gravity might be leaking into extra dimensions that we cannot directly observe, making it appear weak in our three-dimensional space while maintaining comparable strength to other forces when all dimensions are considered. This radical idea suggests that our entire experience of reality might be confined to a tiny slice of a much larger, higher-dimensional universe. Alternative theories propose that the hierarchy problem might be resolved through supersymmetry, a proposed symmetry between matter and force particles that could stabilize the relative strengths of fundamental forces. Yet, despite decades of searching, no direct evidence for supersymmetry has been found, leaving the hierarchy problem as mysterious as ever. The anthropic principle provides another perspective, suggesting that we observe particular force hierarchies because only universes with these specific relationships can support the complex chemistry and long-term stability necessary for life and intelligence to evolve. Perhaps the apparent fine-tuning of force strengths reflects selection bias rather than fundamental physics. Recent discoveries in particle physics and cosmology have revealed new aspects of the hierarchy problem. The discovery of dark energy, which appears to dominate cosmic evolution despite having an energy density 10^120 times smaller than naive theoretical predictions, creates an even more extreme hierarchy problem that makes gravity's weakness seem moderate by comparison. Tonight, we're diving deep into one of physics' most profound mysteries, exploring why the force that shapes planets and galaxies is so incredibly weak compared to the force that holds atoms together. You'll discover exactly how physicists measure and compare fundamental force strengths. Learn about cutting-edge theories that attempt to explain this hierarchy, and explore what the weakness of gravity reveals about the hidden dimensions and exotic physics that might govern our universe. We'll investigate the mathematical frameworks that govern fundamental forces, examine how string theory and extra dimensions might resolve the hierarchy problem, and uncover the role that quantum corrections play in determining the relative strengths of different interactions. You'll learn about experimental tests of gravity as strength and discover how the hierarchy problem connects to some of the deepest questions in cosmology and particle physics. We'll explore unified field theories that attempt to show how all forces emerge from a single underlying interaction, investigate the anthropic implications of force hierarchies for the existence of complex structures in the universe, and examine cutting-edge experiments that are probing the nature of gravity and electromagnetism at the smallest scales. You'll discover how the hierarchy problem drives modern theoretical physics research, from searches for extra dimensions to investigations of quantum gravity, and learn about the cosmological consequences of force hierarchies for the formation and evolution of cosmic structures. This isn't just a story about abstract physics constants and theoretical speculation. This is about understanding why the universe has the particular architecture that allows complexity, structure, and ultimately consciousness to exist. The extreme weakness of gravity compared to electromagnetism shapes everything from the stability of atoms to the lifetime of stars to the possibility of planetary systems that can support life. The hierarchy problem connects to fundamental questions about the nature of space and time, the origin of physical law, and whether the constants we observe are unique or represent one realization among infinite possibilities in a vast multiverse where different regions have different force hierarchies. As we explore why gravity is 1040 times weaker than electromagnetism, you will discover how this seemingly simple numerical ratio opens doorways to some of the most revolutionary ideas in modern physics, from extra dimensions and parallel universes to the possibility that our three-dimensional reality is just a projection from physics operating in high dimensions. If you are fascinated by the deepest mysteries of fundamental physics and how they shape the structure of reality itself, subscribe and hit the thumbs up button. And here is a mind-bending question to consider. If you could adjust the strength of gravity relative to electromagnetism, what would happen to atoms, stars, and planets? If you made gravity just 10 times stronger or weaker than it is now? Comment below with your predictions. I'll pin the most insightful physics reasoning. Now, let's begin our journey into the heart of the hierarchy problem, where we'll discover how the bizarre weakness of gravity reveals hidden truths about the fundamental architecture of our universe. Chapter 1. The Hierarchy Problem. The hierarchy problem represents one of the most profound and disturbing puzzles in theoretical physics, arising from the observation that the fundamental forces of nature exhibit strength differences so extreme they seem to violate any reasonable expectation of how a unified theory should work. The gravitational force is not just weaker than electromagnetic force. It is weaker by a factor so large that it challenges our basic understanding of how the universe could be constructed from unified underlying principles. To understand the magnitude of this hierarchy, consider that in the realm of particle physics, natural scales are typically related to each other by factors of a few, perhaps 10, or occasionally 100. When physicists encounter ratios of thousands or millions, they begin to suspect that new physics or hidden symmetries are at work. But the hierarchy between gravity and electromagnetism involves a ratio of 1040, a number so extraordinarily large that it seems to demand a fundamental explanation. The mathematical expression of this hierarchy emerges when we compare the fundamental constants that govern these forces. Dr. Nima Arkani-Hamd, from the Institute for Advanced Study, explains the conceptual challenge. The hierarchy problem isn't just about large numbers. It's about the apparent impossibility of maintaining such large hierarchies stable against quantum corrections. In quantum field theory, everything wants to mix with everything else. So maintaining a force that's y times weaker than another seems to require impossible fine-tuning. The stability problem emerges when quantum mechanics is applied to theories with large hierarchies. Virtual particles constantly pop in and out of existence throughout the quantum vacuum, and these quantum fluctuations typically generate corrections to physical parameters that are comparable to the highest energy scales in the theory. If the theory includes both gravity and electromagnetism, quantum corrections should naturally drive their strengths towards similar values. This technical naturalness problem suggests that maintaining the observed hierarchy between gravity and electromagnetism requires incredible fine-tuning of parameters, cancellations between different quantum contributions that must be precise to one part in 1040 or more. Such fine-tuning seems highly implausible without some deeper symmetry or mechanism that protects the hierarchy. The hierarchy problem becomes even more acute when we consider the Planck scale, the natural scale where quantum effects and gravitational effects become comparable. At energies around 1019 GeV, corresponding to the Planck energy, quantum gravity effects become important, and all forces might be expected to have comparable strengths. Yet, in our low-energy world, gravity remains extraordinarily weak. String theory attempts to resolve the hierarchy problem by proposing that all fundamental forces arise from different vibrational modes of one-dimensional strings. In string theory's natural units, all forces have comparable strengths, with the apparent weakness of gravity emerging from the compactification of extra dimensions that reduce gravity's effective strength in our three-dimensional space. The IDD model, named after Arkani-Hamd, Dimopoulos, and Valley, proposes a radical solution where gravity only appears weak because it can spread into large extra dimensions, while other forces are confined to our three-dimensional brain. If these extra dimensions are large enough, the fundamental Planck scale could be much lower than previously thought, potentially making quantum gravity accessible to accelerator experiments. Randall-Sundrum models offer an alternative approach using curved extra dimensions where gravity can be exponentially suppressed without requiring large extra dimensions. In these scenarios, we live on a brane in a five-dimensional anti-de Sitter space, and the exponential warping of space-time creates the observed hierarchy naturally. The gauge hierarchy problem represents a related but distinct aspect of the hierarchy puzzle, focusing on why the Higgs boson mass is so much smaller than the Planck scale. This problem led to the prediction of supersymmetry, a proposed symmetry that could protect scalar masses from large quantum corrections by pairing every known particle with a superpartner. Supersymmetric theories naturally address both the gauge hierarchy problem and aspects of the gravity electromagnetism hierarchy by providing cancellation mechanisms that prevent quantum corrections from destroying the delicate balance of force strengths. However, the lack of experimental evidence for supersymmetry has called into question whether this approach correctly solves the hierarchy problem. Environmental selection provides an alternative perspective where the observed hierarchy reflects anthropic selection rather than fundamental physics. In this view, universes with different force hierarchies exist somewhere in a multiverse, but we observe specific ratios because only universes with these particular values can support the complex chemistry necessary for life. The cosmological constant problem represents an even more extreme hierarchy puzzle. involving a ratio of approximately y-day between theoretical predictions and observed values. This makes gravity's YY weakness seem almost reasonable by comparison, suggesting that our understanding of hierarchies in physics remains fundamentally incomplete. Quantum field theory's treatment of hierarchies through renormalization group techniques reveals how force strengths can evolve with energy scale, potentially unifying at very high energies despite their low energy differences. The running of coupling constants provides a framework for understanding how apparent hierarchies might emerge from more symmetric, high-energy physics. The weak force provides an interesting intermediate case in the hierarchy problem. At low energies, the weak force appears much weaker than electromagnetism, but this weakness results from spontaneous symmetry, breaking rather than a fundamental hierarchy. Above the electroweak scale, electromagnetic and weak forces have comparable strengths. Grand unified theories attempt to unify the strong, weak, and electromagnetic forces by showing that they have identical strengths at very high energies, with their low energy differences emerging from symmetry breaking. However, including gravity in such schemes remains extremely challenging due to the enormous hierarchy that must be explained. The holographic principle suggests that the hierarchy problem might reflect our misunderstanding of the fundamental degrees of freedom in physics. If gravity is emergent from more fundamental physics encoded on lower dimensional surfaces, then the apparent weakness of gravity might reflect the emergent nature of spacetime itself. Loop quantum gravity and other approaches to quantum gravity attempt to resolve hierarchy problems by treating spacetime as fundamentally discrete rather than continuous. In these theories, the apparent weakness of gravity might reflect the granular structure of spacetime at the Planck scale. Asymptotic safety scenarios propose that gravity might have a non-trivial fixed point at high energies, potentially allowing it to remain weak at all scales without requiring fine-tuning. This approach suggests that the hierarchy problem might be resolved through the intrinsic dynamics of quantum gravity. The Swammland conjectures from string theory suggest that not all apparently consistent theories of quantum gravity can actually be realized, potentially constraining the possible values of force hierarchies and explaining why we observe particular ratios rather than others. Experimental searches for deviations from Newton's law at short distances have placed increasingly stringent constraints on theories that attempt to explain gravity's weakness through extra dimensions or other exotic mechanisms. These tests probe the fundamental nature of space and force hierarchies. Dark matter and dark energy might provide clues about hierarchy problems if these phenomena reflect new forces or particles with their own hierarchy relationships. Understanding the full spectrum of forces in nature might reveal patterns that explain why gravity appears so extraordinarily weak. Machine learning approaches are being applied to hierarchy problems to identify patterns in the landscape of possible theories and force strengths. These techniques might reveal hidden relationships that explain why particular hierarchies are realized in nature. Future theoretical developments might reveal whether hierarchy problems require new physics beyond the standard model or whether they can be resolved within existing frameworks through better understanding of quantum field theory and general relativity. Dr. Steven Winberg reflects on the hierarchy problem significance. The enormous weakness of gravity compared to other forces suggests that we're missing something fundamental about how physics works. Solving this puzzle might require revolutionary changes in how we think about space, time, forces, and the basic architecture of reality. The hierarchy problem demonstrates how apparently simple observations about force strengths can reveal deep inconsistencies in our understanding of fundamental physics, driving theoretical developments that push the boundaries of human knowledge about the nature of reality. Understanding the hierarchy problem reveals that the weakness of gravity is not just a curious fact about nature, but a profound puzzle that challenges our most basic assumptions about how unified theory should work, pointing toward exotic, physics that might operate beyond our current understanding. Chapter 2. Measuring weakness. Quantifying exactly how much weaker gravity is compared to electromagnetism requires sophisticated experimental techniques and careful theoretical analysis that reveals not only the magnitude of this extraordinary difference, but also its profound implications for our understanding of fundamental physics. The measurement of force strengths involves comparing fundamental constants, analyzing particle interactions, and conducting precision experiments that push the boundaries of what is technically possible while revealing deep truths about the architecture of reality. The most direct comparison between gravitational and electromagnetic forces comes from analyzing the interaction between two elementary particles, such as protons or electrons. When two protons are separated by a distance equal to their classical radius, about 10 to 15 meters, the electromagnetic repulsion between their positive charges is approximately 1,036 times stronger than the gravitational attraction between their masses. However, the full 1,040 factor emerges when we consider the fundamental coupling constants that characterize these forces in the context of quantum field theory. Dr. Carlo Rovelli from Aix-Marseille University, who studies quantum gravity, explains the measurement challenge. Comparing force strengths isn't just about measuring forces directly. It requires understanding how different interactions scale with energy distance and the types of particles involved. The hierarchy becomes most apparent when we compare dimensionless coupling constants that characterize the fundamental strength of each force. The experimental measurement of fundamental constants requires extraordinary precision because these quantities appear in so many different physical processes. The gravitational constant g is actually one of the least precisely known fundamental constants, measured to only about 4 decimal places compared to the electromagnetic fine structure constant, which is known to more than 10 decimal places. Cavendish-type experiments represent the gold standard for measuring gravitational interactions in laboratory settings, using sensitive torsion balances to detect the tiny gravitational forces between massive objects. These experiments must account for electromagnetic and other effects that can overwhelm the weak gravitational signals, requiring sophisticated isolation and control techniques. The weakness of gravity becomes apparent in these experiments through the extraordinary measures needed to detect gravitational effects. While electromagnetic forces between charged objects can be easily measured with simple instruments, detecting gravitational forces requires isolating test masses from all electromagnetic influences and measuring deflections smaller than the width of atomic nuclei. Particle physics experiments reveal the hierarchy through the behavior of elementary particles in different force fields. Charged particles in electromagnetic fields undergo rapid acceleration and energy changes, while the same particles in gravitational fields require enormous masses to produce detectable effects. This difference manifests directly in the design of particle accelerators and detectors. The hierarchy manifests differently at various length scales, providing insights into how force strengths depend on the energy and distance scales being probed. At atomic scales, electromagnetic forces completely dominate gravitational effects, while at astronomical scales, gravity's cumulative effect from enormous masses can overcome electromagnetic forces despite its fundamental weakness. Precision tests of general relativity provide indirect measurements of gravitational coupling strength by comparing theoretical predictions with observations of planetary orbits, gravitational wave emissions, and light deflection by massive objects. These tests confirm that gravity behaves exactly as predicted by Einstein's theory while highlighting its weakness compared to electromagnetic phenomena. Quantum electrodynamics calculations demonstrate electromagnetic force strength through precision predictions of phenomena like the anomalous magnetic moment of electrons and the Lamb shift in atomic energy levels. These calculations involve summing infinite series of quantum corrections that test our understanding of electromagnetic interactions to extraordinary precision. The running of coupling constants with energy scale reveals how force strengths change as we probe higher energy regimes. Electromagnetic interactions become stronger at higher energies, while gravitational interactions also increase. But the enormous hierarchy between them persists across all energy scales accessible to current experiments. Cosmological measurements provide large-scale tests of force hierarchies by observing how electromagnetic and gravitational forces shape the evolution of cosmic structures. The formation of galaxies, stars, and planetary systems reflects the delicate balance between these forces over cosmic timescales. Laboratory tests of Newton's law at short distances probe whether gravity maintains its weakness down to microscopic scales, or whether new physics might emerge that modifies gravitational interactions. These experiments use sophisticated techniques to measure gravitational forces between objects separated by distances smaller than a millimeter. The development of gravitational wave astronomy has enabled direct detection of gravitational effects from some of the most energetic processes in the universe. Yet even these cosmic cataclysms produce gravitational waves that require kilometer-scale laser interferometers to detect, illustrating gravity's fundamental weakness. Atomic physics provides another window into force hierarchies through the relative importance of electromagnetic and gravitational effects in determining atomic structure. While electromagnetic forces determine all chemical and atomic properties, gravitational effects on atoms are so tiny they've never been directly measured, despite decades of increasingly sophisticated experiments. Particle accelerator experiments reveal force hierarchies through the ease with which different forces can be turned on and off. Electromagnetic forces can be manipulated through electric and magnetic fields generated by conventional technology, while gravitational forces require enormous masses and cannot be effectively controlled or shielded. The hierarchy affects the design of all physics experiments because electromagnetic effects must be carefully controlled and eliminated to study other phenomena. Gravitational effects, by contrast, are usually so small they can be ignored except in the most sensitive measurements or astronomical observations. Precision measurement of planetary motion provides tests of gravitational strength over astronomical distances and timescales. The stability of planetary orbits over billions of years reflects the precise balance between gravitational attraction and orbital motion, while electromagnetic effects on planetary dynamics are utterly negligible. High-energy particle physics experiments indirectly probe force hierarchies through the search for new particles and interactions that might explain why gravity is so weak. The Large Hadron Collider and other facilities look for evidence of extra dimensions, supersymmetry, or other exotic physics that could resolve hierarchy problems. The measurement of force hierarchies extends to searches for variations in fundamental constants over cosmic time and distance scales. Astronomical observations of distant quasars and ancient starlight probe whether the relative strengths of forces have changed during cosmic evolution. Quantum gravity experiments using ultra-cold atoms and precision interferometry are beginning to probe the interface between quantum mechanics and gravity, potentially revealing new aspects of how gravitational interactions work at quantum scales where hierarchy problems become most apparent. Tabletop experiments searching for fifth forces or modifications to gravity at short distances provide direct tests of theories that attempt to explain gravity's weakness through extra dimensions or other exotic mechanisms. These experiments can potentially detect new physics that modifies force hierarchies. The development of atomic clocks with unprecedented precision has enabled tests of gravitational effects on time dilation and frequency shifts that were previously unmeasurable, providing new ways to probe the fundamental nature of gravitational interactions. Future experiments using space-based platforms will enable even more sensitive tests of force hierarchies by eliminating terrestrial sources of electromagnetic noise and vibration that limit ground-based measurements of weak gravitational effects. Quantum simulation techniques using cold atoms and photonic systems are being developed to model fundamental force interactions in controlled laboratory settings, potentially providing new insights into how hierarchy problems emerge from underlying physics. The measurement of dark matter interactions provides indirect probes of possible new forces that might help explain hierarchy problems. If dark matter interacts through forces with intermediate strengths between gravity and electromagnetism, it could provide clues about force unification. Dr. Savas Dimopoulos from Stanford University reflects on measuring force hierarchies. Every precision measurement of fundamental constants is really a search for new physics. The extraordinary weakness of gravity compared to electromagnetism suggests that there are aspects of reality we haven't discovered yet, and our measurements are getting sensitive enough to potentially detect them. Measuring the weakness of gravity reveals not just the magnitude of force hierarchies, but also their remarkable stability across different energy scales, experimental conditions, and cosmic environments, highlighting the deep mystery of why such extreme hierarchies persist without any apparent mechanism to maintain them. Understanding how we measure force hierarchies demonstrates the experimental foundation for one of physics' greatest puzzles, while revealing how precision measurements continue to probe the boundaries between known and unknown physics in our quest to understand fundamental reality. Chapter 3: Electromagnetic Dominance. The electromagnetic force as dominance over gravity in the microscopic realm stems from the fundamental properties of electric charge and the mathematical structure of electromagnetic field theory, creating the stable atomic and molecular structures that make chemistry, biology, and all complex matter possible. Understanding why electromagnetism is so powerful compared to gravity reveals deep principles about how forces work in quantum mechanics and why the universe can support the intricate structures we observe throughout nature. The mathematical foundation of electromagnetic strength lies in the fine structure constant alpha approximately equals 1/137th, which characterizes the coupling strength between charged particles and electromagnetic fields. This dimensionless number determines how strongly electric charges interact with photons and appears in calculations of virtually every electromagnetic phenomenon, from atomic energy levels to the scattering of light by matter. In quantum electrodynamics, electromagnetic interactions arise from the exchange of virtual photons between charged particles. The probability amplitudes for these interactions depend on the fine structure constant, with higher order quantum corrections involving powers of alpha. Since alpha approximately equals 0.007, quantum corrections are small but measurable, allowing for precise theoretical predictions and experimental tests. Dr. Freeman Dyson, who developed much of modern quantum electrodynamics, explained the remarkable nature of electromagnetic interactions. The electromagnetic force achieves a perfect balance, strong enough to bind electrons to nuclei and create stable atoms, yet weak enough that quantum mechanics can provide precise, calculable predictions for all electromagnetic phenomena. The photon's masslessness plays a crucial role in electromagnetic dominance by allowing electromagnetic forces to have infinite range without decay. Unlike the weak nuclear force, which is mediated by massive W and Z bosons that limit its range to subatomic distances, electromagnetic forces decrease only as the inverse square of distance, enabling long-range interactions between charged objects. Atomic structure demonstrates electromagnetic dominance through the precise energy levels that arise from electron-nucleus interactions. The Bohr model, later refined by quantum mechanics, shows how electromagnetic forces create discrete atomic orbits whose energies depend only on the fine structure constant and fundamental physical constants, with gravitational effects utterly negligible. The binding energy of atoms illustrates electromagnetic strength quantitatively. A typical atomic binding energy is on the order of electron volts eV, while the gravitational binding energy of an electron to a proton is approximately 10 to 40 electron volts, completely insignificant compared to electromagnetic effects. This enormous difference explains why chemistry is governed entirely by electromagnetic interactions. Chemical bonding represents one of nature's most important manifestations of electromagnetic dominance. Whether ionic bonds formed by electrostatic attraction between oppositely charged ions, covalent bonds created by shared electron pairs, or van der Waals forces arising from quantum mechanical charge fluctuations, all chemical phenomena emerge from electromagnetic interactions operating at the atomic scale. The stability of matter depends fundamentally on electromagnetic dominance over gravity at microscopic scales. If gravity were comparable to electromagnetism at atomic distances, the quantum mechanical uncertainty principle would prevent stable atomic orbits, making atoms collapse or become unstable in ways that would prevent the existence of chemistry and complex matter. Molecular structures arise from electromagnetic forces, creating specific geometric arrangements that minimize electrostatic energy while satisfying quantum mechanical constraints. The precise shapes of molecules, linear, bent, tetrahedral, octahedral, all emerge from electromagnetic interactions between electrons and nuclei following the principles of quantum chemistry. Electromagnetic radiation provides the mechanism through which atoms and molecules can emit and absorb energy, enabling the complex energy transfer processes that power everything from photosynthesis to stellar nucleosynthesis. The interaction between matter and light involves electromagnetic coupling that determines absorption and emission spectra. The electromagnetic spectrum spans an enormous range of frequencies and energies, from low-energy radio waves to high-energy gamma rays, all representing different manifestations of electromagnetic field oscillations. This vast spectrum enables the diverse electromagnetic phenomena we observe in nature and technology. Electromagnetic forces in condensed matter create the electronic properties that govern the behavior of solids, liquids, and gases. Electrical conductivity, thermal conductivity, optical properties, and magnetic behavior all arise from electromagnetic interactions between electrons and atomic nuclei in different material configurations. The quantum Hall effect demonstrates electromagnetic dominance through the precise quantization of electrical resistance in two-dimensional electron systems, subjected to strong magnetic fields. This phenomenon reveals deep connections between electromagnetic topology and quantum mechanics that have revolutionized our understanding of condensed matter physics. Superconductivity represents an exotic electromagnetic phenomenon where electrical resistance vanishes completely due to quantum mechanical pairing of electrons. The formation of Cooper pairs and their collective behavior illustrate how electromagnetic interactions can create macroscopic quantum states with extraordinary properties. Electromagnetic waves propagating through vacuum carry energy and momentum according to Maxwell's equations, demonstrating how electromagnetic fields can exist independently of matter. The wave-particle duality of light reveals electromagnetic radiation as fundamental quantum mechanical nature while maintaining its classical wave properties. The electromagnetic force S-gauge symmetry provides deep insights into its mathematical structure through the principle of local gauge invariance. This symmetry principle not only determines the form of Maxwell's equations, but also connects electromagnetic theory to fundamental principles of quantum field theory and particle physics. Electromagnetic vacuum fluctuations create measurable effects like the Casimir force between closely spaced conducting plates. These quantum effects demonstrate that even empty space contains electromagnetic energy that can influence physical systems, revealing the richness of quantum electromagnetic phenomena. The interaction between electromagnetic fields and charged particle beams enables technologies from television tubes to particle accelerators. The ability to control and manipulate electromagnetic fields with high precision has made possible the entire technological civilization based on electronics and electromagnetic devices. Electromagnetic forces in biological systems enable the complex chemistry of life through precise molecular interactions. Protein folding, DNA replication, cellular signaling, and metabolic processes all depend on electromagnetic forces operating at the molecular level with extraordinary specificity and efficiency. The planetary magnetosphere demonstrates electromagnetic dominance over gravity in protecting Earth's atmosphere from solar wind. While gravity holds the atmosphere in place, electromagnetic forces deflect charged particles that would otherwise strip away atmospheric gases, showing how both forces contribute to habitability. Electromagnetic induction, described by Faraday's law, enables the generation of electrical power through mechanical motion in magnetic fields. This phenomenon powers virtually all electrical generation systems and demonstrates how electromagnetic forces can convert between different forms of energy with high efficiency. The electromagnetic force's role in stellar physics involves the electromagnetic pressure that helps support stars against gravitational collapse, particularly in white dwarf stars, where electron degeneracy pressure provides the primary support mechanism. This shows how electromagnetic quantum effects can compete with gravity even at stellar scales. Quantum electrodynamics calculations of the electron magnetic moment represent one of the most precise theoretical predictions ever made, agreeing with experiment to more than 10 decimal places. This extraordinary precision demonstrates the fundamental consistency and power of electromagnetic theory. Electromagnetic forces in particle accelerators enable the detection and study of subatomic particles by deflecting charged particles through known electromagnetic fields. The precise control of electromagnetic forces makes possible the experiments that probe the fundamental structure of matter and energy. The electromagnetic coupling constant's apparent constancy across cosmic time and space has been tested through astronomical observations of distant quasars and ancient light. These tests confirm that electromagnetic interactions maintain their strength throughout cosmic evolution, supporting the fundamental nature of electromagnetic dominance. Future technologies may exploit exotic electromagnetic phenomena like metamaterials with negative refractive indices or plasmonic effects that concentrate electromagnetic energy at nanometer scales. These developments demonstrate the continued discovery of new ways that electromagnetic forces can be controlled and applied. Dr. Richard Feynman reflected on electromagnetic dominance. All of chemistry and most of physics is just applied electromagnetism. The electromagnetic force creates the rich complexity we see in matter while remaining simple enough that we can calculate its effects precisely using quantum field theory. Electromagnetic dominance over gravity at microscopic scales enables the existence of stable atoms, complex chemistry, and ultimately life itself, while the mathematical structure of electromagnetic theory provides one of our most successful and precise descriptions of fundamental physical phenomena. Understanding electromagnetic dominance reveals why this force shapes all the familiar properties of matter and energy that we experience directly, while gravity's weakness ensures that it doesn't interfere with the delicate quantum mechanical processes that create atomic and molecular complexity. Chapter 4. Gravitational Puzzles. The extreme weakness of gravity compared to other fundamental forces creates a cascade of puzzles that challenge our understanding of how this most familiar force fits into the broader framework of physics. From theoretical problems with unification to experimental challenges in measurement, gravity's feebleness raises profound questions about the fundamental structure of reality and why this particular force appears to be so dramatically different from electromagnetism, weak nuclear, and strong nuclear interactions. The naturalness problem represents perhaps the most troubling aspect of gravity's weakness from a theoretical perspective. In quantum field theory, we expect physical parameters to be natural, meaning they shouldn't require extraordinary fine-tuning to maintain their observed values. Yet gravity's weakness appears to demand precisely such fine-tuning. with quantum corrections threatening to drive its strength toward much larger values. When physicists calculate quantum corrections to gravitational interactions, they find contributions that should make gravity much stronger than observed. Virtual particles constantly appearing and disappearing in quantum vacuum fluctuations should generate corrections to gravitational coupling that are comparable to other fundamental force strengths. Yet these corrections must somehow be cancelled to maintain gravity's observed weakness. Dr. Steven Weinberg, who won the Nobel Prize for work on electroweak unification, articulated the gravity puzzle. Gravity is not just weak. It is so extraordinarily weak that maintaining this weakness against quantum correction seems to require conspiratorial cancellations that have no natural explanation within our current theoretical framework. The problem becomes acute when we consider the Planck scale, where quantum gravity effects should become important. At energies around 1019 GeV, corresponding to distances of 10 to 35 meters, quantum fluctuations of spacetime itself should become significant. Yet somehow, gravity remains weak even when we extrapolate to these extreme scales. The cosmological constant problem represents an even more extreme version of gravity's puzzle. Einstein's equations allow for a constant energy density throughout space that would act like gravity, but with repulsive rather than attractive effects. Quantum field theory predicts this constant should be enormous, about 10,120 times larger than observations allow. This cosmological constant discrepancy makes gravity's YY weakness seem almost reasonable by comparison. The fact that both problems involve gravity suggests they might be related, but no convincing theoretical framework has emerged that explains both hierarchies simultaneously. General relativity itself provides clues about gravity's unusual nature through its geometric interpretation. Unlike other forces that act within spacetime, gravity is spacetime, the curvature of the four-dimensional continuum in which all physics takes place. This geometric nature might explain why gravity behaves so differently from other forces. The equivalence principle, which states that gravitational and inertial effects are locally indistinguishable, reveals gravity's unique relationship to spacetime geometry. This principle has no analog in electromagnetic theory or nuclear physics, suggesting that gravity operates according to fundamentally different principles than other forces. Renormalization problems plague attempts to create quantum theories of gravity because Einstein's theory is non-renormalizable. Quantum corrections generate infinite results that cannot be removed through standard techniques. This mathematical difficulty might be connected to gravity's weakness, suggesting that quantum gravity requires entirely new theoretical approaches. String theory attempts to resolve gravity's puzzles by treating all particles and forces as different vibrational modes of one-dimensional strings. In string theory's natural units, all forces have comparable strengths, with gravity's apparent weakness emerging from the compactification of extra dimensions that dilute gravitational effects in our observed three-dimensional space. Loop quantum gravity provides an alternative approach where spacetime itself is quantized into discrete units at the Planck scale. In this framework, gravity's weakness might emerge from the averaging of quantum gravitational effects over scales much larger than the fundamental Planck length. The emergence paradigm suggests that gravity might not be fundamental, but rather an emergent property of more basic physics, similar to how thermodynamics emerges from statistical mechanics. If gravity emerges from underlying degrees of freedom, its weakness might reflect the approximate nature of this emergence. Asymptotic safety represents another approach where gravity might remain finite and calculable at all energy scales through the existence of a non-trivial fixed point in the theory's renormalization group flow. This could potentially resolve both gravity's weakness and its non-renormalizability simultaneously. Extra-dimensional theories provide concrete mechanisms for gravity's weakness through scenarios where gravity can propagate in additional spatial dimensions while other forces remain confined to our three-dimensional space. If these extra dimensions are large or warped in specific ways, gravity could appear weak while maintaining comparable strength to other forces in higher dimensions. The ADB model proposes that gravity only appears weak because it spreads out into large extra dimensions, potentially making the fundamental Planck scale much lower than previously thought. This could make quantum gravity effects accessible to current or near-future experiments. Randall-Sundrum models use curved extra dimensions to exponentially suppress gravity's apparent strength through warping of the extra-dimensional spacetime. These models can explain gravity's weakness without requiring large extra dimensions, potentially resolving several puzzles simultaneously. Anthropic reasoning provides a different perspective on gravity's weakness by suggesting that we observe this particular hierarchy because only universes with such force relationships can support complex chemistry and life. Perhaps gravity's weakness is selected by observational bias rather than explained by fundamental physics. Modified gravity theories attempt to explain apparent gravitational weakness by proposing that Einstein's general relativity is modified at large distances or small accelerations. These theories could potentially explain both gravity's weakness and phenomena like dark matter and dark energy. The hierarchy problem connects gravity's weakness to other mysteries in particle physics, particularly the question of why the Higgs boson mass is so much smaller than the Planck scale. Supersymmetry was proposed to solve this related hierarchy problem, but the lack of experimental evidence has called this approach into question. Dark energy's apparent weakness creates an even more extreme hierarchy problem than gravity itself. The observed dark energy density is about Y-29 grams per cubic centimeter, far smaller than any natural scale in particle physics, suggesting that multiple hierarchy problems might need to be solved simultaneously. Precision tests of general relativity continue to confirm Einstein's predictions, while revealing no deviations that might explain gravity's weakness. These tests probe everything from planetary orbits to gravitational wave emission, finding perfect agreement with general relativity across enormous ranges of distance and timescales. The weak field limit of general relativity reduces to Newtonian gravity, which has been tested with extraordinary precision in laboratory settings. These tests confirm gravity's weakness while searching for deviations that might indicate new physics operating at short distances. Tidal effects demonstrate gravity's weakness through their extreme sensitivity to distance. While electromagnetic forces between charged objects can be easily measured, gravitational tidal effects require sophisticated instruments and careful isolation from other forces to detect, highlighting gravity's feeble nature. Gravitational wave astronomy has opened new windows into gravity's behavior under extreme conditions, revealing how this weak force operates during the most energetic gravitational phenomena in the universe. Even black hole mergers produce gravitational waves so weak they require kilometer-scale detectors to observe. The search for quantum gravity effects in laboratory settings represents one approach to understanding gravity's weakness through direct experimentation. These experiments probe whether quantum mechanical principles apply to gravitational interactions and whether new physics emerges at the interface between quantum mechanics and gravity. Future space-based experiments may provide new insights into gravity's weakness by enabling tests of gravitational physics in environments free from terrestrial electromagnetic interference. These missions could detect subtle gravitational effects that reveal new aspects of how gravity relates to other forces. Dr. Juan Maldacena from the Institute for Advanced Study reflects on gravitational puzzles. Gravity's weakness is telling us something profound about the structure of reality. Whether through extra dimensions, emergent spacetime, or entirely new physics, understanding why gravity is so weak will likely revolutionize our understanding of the universe's fundamental architecture. The puzzles surrounding gravity's weakness continue to drive theoretical Developments and experimental innovations as physicists seek to understand why this most familiar force remains so mysterious and whether its weakness points toward new physics beyond our current understanding. Understanding gravitational puzzles reveals that the weakness of gravity is not just a curious fact about nature, but a profound clue about hidden aspects of reality that might include extra dimensions, emergent spacetime, or entirely new principles governing fundamental interactions. Chapter 5. Extra dimensions. The possibility that our universe contains hidden spatial dimensions beyond the three we directly experience offers one of the most elegant and radical solutions to gravity's weakness puzzle. In these higher dimensional scenarios, gravity might only appear weak because it can spread out into extra dimensions, while other forces remain trapped in our familiar three-dimensional space, creating the observed hierarchy through geometric dilution rather than fundamental differences in force strength. The mathematical foundation for extra dimensions emerged from attempts to unify gravity with other fundamental forces in the early 20th century. Theodore Kaluza and Oscar Klein proposed in the 1920s that electromagnetism and gravity could be unified if space possessed one additional dimension beyond Einstein's four-dimensional spacetime, with this extra dimension curled up at every point in space. Modern string theory requires extra dimensions to be mathematically consistent, typically demanding a total of 10 or 11 dimensions for superstring theories. These extra dimensions must be compactified, curled up, or hidden in ways that make them unobservable at ordinary energy scales, while still influencing the physics we can observe. Dr. Lisa Randall from Harvard University, who pioneered research into extra-dimensional solutions to hierarchy problems, explains the basic concept. Imagine living on a two-dimensional surface like a tabletop. If gravity could spread into the third dimension while you remained stuck to the surface, gravitational forces would appear much weaker to you than they actually are in the full three-dimensional space. The Arkingham-Dimopoulos-Valley (ADD) model proposes that gravity appears weak because it propagates in large extra dimensions, while standard model particles are confined to our three-dimensional brain. If these extra dimensions are large enough, potentially even millimeter-sized, the fundamental Planck scale could be much lower than the apparent 1019 GeV. In ADD scenarios, the weakness of gravity emerges through geometric dilution. Gravitational field lines can spread out into the extra dimensions, reducing the gravitational flux that passes through our three-dimensional space. The apparent weakness depends on the number and size of extra dimensions, with larger dimensions creating weaker apparent gravity. The mathematical description of this dilution involves Gauss's law for gravity in higher dimensions. In our familiar three-dimensional space, gravitational field strength falls off as 1r², but in higher dimensions, it falls off more rapidly. When averaged over the extra dimensions, this creates the 1r² behavior we observe while reducing the overall strength. Randall-Sundrum models provide an alternative approach using curved rather than flat extra dimensions. These models employ five-dimensional anti-de Sitter spacetime with two four-dimensional boundaries or branes. The warping of the extra dimension can exponentially suppress gravity's apparent strength without requiring large extra dimensions. In Randall-Sundrum Type 2 models, we live on a four-dimensional brane embedded in five-dimensional anti-de Sitter space that extends infinitely in the extra dimension. The exponential warping of this space causes gravity to be localized near the brane while still allowing for the observed weak gravitational interactions. The hierarchy problem finds natural resolution in warped extra dimensions because the exponential suppression of mass scales can generate the observed hierarchy between the Planck scale and electroweak scale without fine-tuning. The warping factor can naturally produce ratios as large as 1016 or more. Extra-dimensional scenarios make specific predictions about deviations from Newton's law of gravity at short distances. If gravity becomes strong in extra dimensions at some characteristic scale, We should observe deviations from the inverse square law when probing distances comparable to the size of extra dimensions. Laboratory tests of Newton's law have probed gravitational interactions down to distances of tens of micrometers, placing stringent constraints on large extra-dimension scenarios. These experiments use sophisticated torsion balance techniques to measure gravitational forces between small masses with extraordinary precision. The Large Hadron Collider and other high-energy particle experiments search for signatures of extra dimensions through missing energy events where particles escape into extra dimensions or through the production of Kaluza-Klein resonances, excited states of ordinary particles that would exist if extra dimensions were accessible at high energies. Gravitational wave astronomy provides new opportunities to test extra-dimensional theories through the propagation of gravitational waves in higher dimensional spacetime. Extra dimensions could modify gravitational wave dispersion relations or create additional polarization modes that would be observable with sufficiently sensitive detectors. String compactification creates complex geometries for extra dimensions that determine the low-energy physics we observe. Different compactification schemes can produce different numbers of particle families, different force strengths, and different relationships between fundamental constants. The landscape of string theory contains vast numbers of possible compactifications, each corresponding to different vacuum states with different physical properties. This multiplicity might explain why we observe particular force hierarchies, if different. Regions of the multiverse correspond to different compactifications. Flux compactifications use background electromagnetic and other fields to stabilize extra dimensions at particular sizes and shapes. The interplay between these fluxes and the geometry of extra dimensions determines the effective four-dimensional physics, including force hierarchies and particle masses. Warped product spaces provide frameworks where different regions of extra dimensions can have different geometric properties. These spaces can create effective four-dimensional theories with multiple scales without requiring large hierarchies to be put in by hand. Brownian scenarios place all standard model particles on a four-dimensional brane embedded in higher dimensional space, while gravity propagates throughout the full higher dimensional volume. This setup naturally explains why we observe three spatial dimensions despite the existence of additional dimensions. The radiant field, which describes the size of extra dimensions, can have important cosmological consequences if its value changes over time. Variations in extra-dimensional geometry could affect fundamental constants and potentially explain some puzzling features of cosmic evolution. Supersymmetric extra dimensions provide additional structure that can help stabilize compactifications and relate the geometry of extra dimensions to particle physics through supersymmetric partner relationships between geometric moduli and matter fields. Universal extra dimensions represent scenarios where all particles can propagate in extra dimensions, not just gravity. These theories predict rich spectra of Kaluza-Klein partner particles that could be detected in high-energy experiments if the compactification scale is sufficiently low. Dark matter candidates naturally emerge from extra-dimensional theories through Kaluza-Klein partner particles that could be stable and weakly interacting. The lightest Kaluza-Klein particle in universal extra-dimension models provides a potential dark matter candidate with distinctive properties. Cosmological evolution in extra-dimensional scenarios can differ significantly from standard cosmology through modifications to the Friedmann equation that governs cosmic expansion. Extra-dimensional effects could affect Big Bang nucleosynthesis, structure formation, and other cosmological processes. The stabilization of extra dimensions represents a crucial challenge because quantum corrections and classical instabilities tend to cause extra dimensions to either collapse or expand exponentially. Understanding how extra dimensions maintain constant size requires sophisticated analysis of higher dimensional field dynamics. Black holes in extra dimensions exhibit rich and complex behavior that could potentially be studied through gravitational wave astronomy or high-energy particle collisions. These higher-dimensional black holes could provide signatures of extra dimensions through their distinctive properties. Future experiments may probe extra dimensions through precision tests of gravity at ever smaller distance scales. High-energy particle collisions that access Kaluza-Klein resonances, or astronomical observations that detect extra-dimensional effects in cosmic phenomena. The phenomenology of extra dimensions continues to evolve as theoretical understanding advances and experimental constraints become more stringent. Different extra-dimensional scenarios make different predictions for observable phenomena, allowing experimental tests to distinguish between competing theories. Dr. Raymond Sundram from the University of Maryland reflects on extra dimensions. The idea that space has more dimensions than we can see directly is both ancient and modern. Ancient because humans have always wondered about hidden aspects of reality, and modern because we now have mathematical frameworks and experimental techniques to test these ideas rigorously. Extra dimensions provide compelling potential explanations for gravity's weakness while making testable predictions that continue to be probed by experimental and observational studies, demonstrating how theoretical speculation can lead to concrete scientific investigations of reality's hidden structure. Understanding extra-dimensional solutions to the hierarchy problem reveals how our three-dimensional experience might be just a small slice of a much larger and more complex higher-dimensional reality, where gravity maintains its full strength while appearing weak in our confined domain. Chapter 6. String Theory Insights. String theory provides the most comprehensive and mathematically sophisticated framework for understanding why gravity appears 1040 times weaker than electromagnetism by treating all fundamental particles and forces as different vibrational modes of one-dimensional strings. This revolutionary approach suggests that the hierarchy between forces emerges from the geometry of extra dimensions and the way strings couple to these dimensions, potentially resolving one of physics' most profound puzzles while revealing deep connections between geometry, quantum mechanics, and fundamental interactions. The foundation of string theory's approach to force hierarchies lies in the recognition that at the most fundamental level, there is only one type of object, the string, and all apparent particles and forces arise from different ways this string can vibrate. In this framework, the apparent weakness of gravity compared to electromagnetism reflects differences in how gravitational and electromagnetic modes couple to the compactified extra dimensions. In string theory, gravity emerges from the vibrational mode of closed strings known as the graviton, while electromagnetic forces arise from the photon mode. The coupling strengths of these different modes to matter depend on how the extra dimensions are shaped and what background fields exist in those dimensions, providing a geometric explanation for force hierarchies. Dr. Edward Witten from the Institute for Advanced Study, who has made fundamental contributions to string theory, explains the unified perspective. String theory shows us that all forces are really different aspects of the same underlying stringy physics. The apparent hierarchy between gravity and electromagnetism emerges from the specific way that our three-dimensional world is embedded in the full 10 or 11-dimensional string theory space. The dilatant field in string theory plays a crucial role in determining force hierarchies. This field, which has no analog in ordinary quantum field theory, determines the overall strength of string interactions and can vary throughout spacetime. The value of the dilatant field in our region of space affects the relative coupling strengths of different forces. String compactification on Calabi-Yau manifolds or other complex geometric spaces determines the low-energy physics that we observe, including the hierarchy between force strengths. Different compactification geometries produce different relationships between fundamental forces, potentially explaining why we observe the specific hierarchy that characterizes our universe. The string landscape contains an enormous number of possible vacuum states, estimated to be 10,500 or more, each corresponding to different compactification geometries and different relationships between force strengths. This vast landscape might explain force hierarchies through environmental selection rather than fundamental principles. In string theory, the fundamental scale, the string scale, sets the natural energy where all forces have comparable strength. The apparent weakness of gravity in a low-energy world emerges from the relationship between this string scale and the compactification scale of extra dimensions. Type 2 string theories naturally incorporate both open and closed strings, with open strings giving rise to gauge forces like electromagnetism and closed strings producing gravity. The different boundary conditions and topological properties of these string types can create natural hierarchies between the forces they generate. Heterotic string theory provides frameworks where gauge forces and gravity arise from different sectors of the theory with different coupling strengths. The heterotic construction naturally incorporates both supersymmetry and grand unification while potentially explaining force hierarchies through the specific structure of these theories. M-theory, which unifies different string theories in 11 dimensions, offers additional perspectives on force hierarchies through the dynamics of membranes, branes, and the geometry of the 11th dimension. The relative positions and properties of branes can determine the effective force strengths observed in lower dimensional physics. Warped product spaces in string theory, particularly ADS times SN related geometries, provide concrete realizations of the Randall-Sundrum mechanism for generating force hierarchies. The warping of anti-day Sitter space can exponentially suppress certain coupling constants while leaving others unsuppressed. The DSCFT correspondence, one of string theory's most important discoveries, relates gravitational physics in curved spacetime to non-gravitational quantum field theories on the boundary. This duality provides new tools for understanding how force hierarchies emerge and how apparent weaknesses in bulk gravity relate to boundary physics. Flux compactifications in string theory use background field strengths to stabilize extra dimensions and determine low-energy physics. The interplay between different flux fields can create hierarchies between force strengths while maintaining the overall consistency of the compactified theory. D-brane physics in string theory provides concrete realizations of scenarios where different forces are localized to different regions of space. Standard model particles might be confined to a D-brane while gravity propagates throughout the full higher dimensional space, naturally explaining gravitational weakness. Intersecting brane scenarios create rich phenomenological possibilities where different particle types arise at the intersections of various branes. The geometry of these intersections and the angles between branes can determine the coupling strengths of different interactions. String cosmology explores how force hierarchies evolve during cosmic evolution, particularly during inflationary epochs where the geometry of extra dimensions might change dramatically. These cosmological processes could establish the force hierarchies we observe today through dynamical mechanisms. The holographic principle, which emerged from string theory insights, suggests that all physics in any region can be encoded on its boundary. This principle might indicate that apparent force hierarchies in the bulk emerge from boundary dynamics where all forces have comparable strength. Non-supersymmetric string models face significant challenges in maintaining stability, but they also provide frameworks where hierarchies can arise more naturally without the protection mechanisms that supersymmetry provides. Understanding these models might reveal how hierarchies emerge in more realistic scenarios. String field theory attempts to provide a completely off-shelf formulation of string theory that could address questions about force hierarchies through first principles calculations. While technically challenging, string field theory might eventually provide definitive answers about why particular force hierarchies emerge. Topological string theory focuses on the topological aspects of string compactifications and provides tools for computing certain physical quantities exactly. These approaches might reveal topological origins for force hierarchies that are protected against quantum corrections. Matrix models provide non-perturbative definitions of certain string theories and offer alternative perspectives on how force hierarchies might emerge from the fundamental dynamics of matrices rather than from geometric compactification effects. Black holes in string theory exhibit rich structures that depend on both the compactification geometry and the hierarchy between force strengths. Understanding string theory black holes might provide insights into how force hierarchies affect gravitational phenomena in extreme regimes. Precision tests of string theory predictions remain challenging because the theory typically operates at energy scales far above what current experiments can reach. However, certain low-energy consequences of string theory could potentially be tested through measurements of force hierarchies and their variations. Machine learning techniques are being applied to string theory to explore the landscape of possible compactifications and identify patterns that might explain observed force hierarchies. These approaches might reveal hidden relationships in the vast space of string theory solutions. Swampland conjectures attempt to identify which effective field theories can actually be embedded in consistent theories of quantum gravity, like string theory. These conjectures might constrain possible force hierarchies and explain why certain relationships between force strengths are realized in nature. The cosmological constant problem takes on new dimensions in string theory because the theory provides mechanisms for generating both positive and negative contributions to the cosmological constant. Understanding how these contributions balance or fail to balance remains one of string theory's greatest challenges. Future developments in string theory might provide more definitive explanations for force hierarchies through better understanding of string dynamics, improved techniques for analyzing compactifications, or discovery of new dualities that relate apparently different physical regimes. Experimental signatures of string theory might emerge through precision tests of gravitational interactions, searches for extra dimensions, or discovery of supersymmetric particles. Any of these findings could provide support for string theory's approach to understanding force hierarchies. Dr. Joseph Polchinski, who made fundamental contributions to string theory, reflected on its approach to hierarchies. String theory provides a remarkably rich and constrained framework for understanding force hierarchies. While we haven't yet pinpointed exactly why gravity is so weak, the theory gives us powerful tools and suggests that the answer involves the deepest aspects of geometry and quantum mechanics. String theory insights reveal that force hierarchies might emerge from the fundamental geometry of higher dimensional spaces, rather than being arbitrary features of low-energy physics, suggesting that understanding the shape of extra dimensions could explain some of physics' most puzzling numerical relationships. Understanding string theory's approach to force hierarchies demonstrates how the most abstract mathematical concepts in modern physics might hold keys to explaining some of the most basic and puzzling features of the natural world we observe. Chapter 7. Quantum corrections. Quantum mechanical effects fundamentally alter our understanding of force hierarchies by introducing virtual particle fluctuations, loop corrections, and renormalization group evolution that can dramatically modify the apparent strengths of fundamental interactions. These quantum corrections reveal why maintaining a stable hierarchy between gravity and electromagnetism presents such profound theoretical challenges, and how quantum effects might either explain or exacerbate the mystery of gravity's extraordinary weakness. The foundation of quantum corrections lies in the uncertainty principle, which allows virtual particles to spontaneously appear and disappear from the quantum vacuum, provided they do so within timescales permitted by energy-time uncertainty relations. These virtual particles create loops in Feynman diagrams that contribute corrections to fundamental force strengths, potentially disrupting any classical hierarchy between different interactions. In quantum electrodynamics, loop corrections modify the fine structure constant alpha through processes where virtual electron-positron pairs screen the electric charge of particles. These corrections are logarithmic in energy scale, causing alpha to increase slowly as we probe higher energies, an effect confirmed through precision experiments at particle accelerators. Dr. Kenneth Wilson, who won the Nobel Prize for developing renormalization group theory, explained the significance of quantum corrections. Virtual particles don't just provide small corrections to classical physics. They fundamentally determine how forces behave at different energy scales and reveal deep connections between apparently unrelated phenomena. The renormalization group describes how coupling constants change with energy scale through quantum corrections. Different forces exhibit different rates of running, with the strong force becoming weaker at higher energies, while electromagnetic and weak forces become stronger, potentially converging at some unification scale. Grand unified theories exploit this running of coupling constants to show how the electromagnetic, weak, and strong forces might have identical strengths at very high energies around 1016 GeV, despite their very different low energy values. However, including gravity in such schemes remains problematic due to its extreme weakness. The hierarchy problem emerges most acutely when we consider quantum corrections to scalar field masses, particularly the Higgs boson. Virtual particle loops involving every particle in the Standard Model contribute to the Higgs mass, and these contributions should naturally be of order the Planck scale unless they are cancelled with extraordinary precision. Supersymmetry was proposed as a solution to the hierarchy problem by providing cancellation mechanisms where fermionic and bosonic loop contributions cancel each other, preventing runaway quantum corrections that would destabilize force hierarchies. Each Standard Model particle would have a superpartner with opposite quantum statistics. However, the lack of experimental evidence for supersymmetry, despite extensive searches at the Large Hadron Collider, has raised questions about whether this approach correctly addresses hierarchy problems. If supersymmetry exists, it must be broken in ways that still provide adequate cancellations. Dimensional transmutation provides a quantum mechanical mechanism where dimensionless coupling constants can generate dimensional quantities through loop effects. This process might explain how hierarchies between different mass scales arise from fundamental physics that is, scale invariant at the classical level. The cosmological constant problem represents an extreme example of quantum correction difficulties, where zero-point energy contributions from all quantum fields should generate a vacuum energy density 10,120 times larger than observed. This makes the gravity hierarchy problem seem mild by comparison. Effective field theory approaches recognize that quantum corrections depend on the energy scale being probed and the unknown physics that might exist at higher energies. Different assumptions about high-energy physics lead to different predictions for low-energy force hierarchies. Loop quantum gravity provides a discrete approach to quantum corrections in gravitational physics by treating space-time itself as quantized at the Planck scale. In this framework, quantum corrections to gravitational interactions might behave very differently than in continuous space-time. Asymptotic safety scenarios propose that gravity might remain finite and calculable at all energy scales through the existence of a non-trivial fixed point where quantum corrections exactly balance classical scaling. This could potentially resolve both hierarchy problems and gravity's non-renormalizability. String theory handles quantum corrections through its extended structure, where strings have finite size rather than being point particles. This extension regulates the divergences that plague point particle theories and might provide natural explanations for why certain force hierarchies are stable. The ADS-CFT correspondence has revealed that strongly coupled quantum field theories can be equivalent to classical gravity in higher dimensions. This duality suggests that quantum corrections in field theory might correspond to classical geometry in gravitational theories. Holographic renormalization provides techniques for computing Quantum corrections engage theories through their gravitational duals, potentially offering new insights into how force hierarchies are affected by quantum effects and how they might be stabilized. Critical phenomena and phase transitions in quantum field theory demonstrate how quantum corrections can generate or destroy hierarchies between different energy scales. Understanding these transitions might provide insights into how cosmic force hierarchies emerged during the early universe. The trace anomaly in quantum field theory shows how quantum corrections can break classical scale invariance, potentially providing mechanisms for generating hierarchies from theories that are scale invariant at the classical level. Quantum corrections in curved spacetime introduce additional complexities because the background geometry affects virtual particle propagation. These effects might be relevant for understanding how force hierarchies behave during cosmic evolution or in strong gravitational fields. The Casimir effect demonstrates that quantum corrections have measurable consequences for electromagnetic forces between conducting surfaces. This shows that virtual particle effects are not just theoretical constructs, but have observable implications for force measurements. Precision tests of quantum electrodynamics through measurements of the electron magnetic moment provide extraordinary confirmations that quantum corrections operate exactly as predicted by theory. These tests verify our understanding of how quantum effects modify electromagnetic interactions. Electroweak unification relies crucially on quantum corrections that cause electromagnetic and weak coupling constants to converge at the electroweak scale around 100 GeV. This demonstrates how quantum effects can reveal hidden unifications between apparently different forces. The running of the strong coupling constant has been measured precisely through deep inelastic scattering and other high-energy experiments, confirming that quantum corrections behave as predicted by quantum chromodynamics and approach asymptotic freedom at high energies. Anomaly cancellation conditions in quantum field theory place stringent constraints on which combinations of particles can exist consistently. These constraints might help explain why certain force hierarchies are realized while others are forbidden. Quantum corrections to neutrino masses through seesaw mechanisms provide examples of how loop effects can generate extremely small mass scales from natural high-energy parameters, potentially offering templates for understanding how gravitational weakness might emerge. Non-commutative geometry provides frameworks where quantum corrections modify spacetime geometry itself, potentially affecting how force hierarchies are defined and maintained. These approaches might reveal connections between quantum mechanics and gravitational physics. Machine learning techniques are being applied to understand patterns in quantum corrections and their effects on force hierarchies. These approaches might reveal hidden relationships that could explain why particular hierarchies are stable against quantum effects. Future calculations of quantum corrections in quantum gravity theories might reveal whether the extreme weakness of gravity can be maintained against quantum effects, or whether new physics is required to stabilize force hierarchies. Experimental tests of quantum corrections continue through precision measurements of fundamental constants, searches for new particles that could affect loop calculations, and studies of quantum effects in increasingly controlled laboratory environments. The development of quantum error correction principles might provide new insights into how nature maintains stable force hierarchies against the disruptive effects of quantum fluctuations, potentially revealing new symmetries or protection mechanisms. Dr. Frank Wilczek reflects on quantum corrections and hierarchies. Quantum mechanics teaches us that nothing is really constant. Every parameter in physics receives corrections from virtual particle effects. Understanding how force hierarchies survive these corrections, or whether they require new physics to remain stable, is one of the deepest challenges in theoretical physics. Quantum corrections reveal that the hierarchy between gravity and electromagnetism is not a static feature of nature, but a dynamic balance that must be maintained against the disruptive effects of virtual particle fluctuations, highlighting the deep mystery of how such extreme hierarchies can remain stable. Understanding quantum corrections and their role in force hierarchies demonstrates how the quantum nature of reality introduces both profound theoretical challenges and potential solutions to some of physics' most puzzling features, showing how virtual particles shape the structure of fundamental interactions. Chapter 8. Anthropic Reasoning. The anthropic principle provides a radically different perspective on gravity's weakness by suggesting that we observe this particular hierarchy not because of fundamental physics principles, but because only universes with these specific force relationships can support the complex chemistry, stable stellar evolution, and long-term cosmic development necessary for life and consciousness to emerge. This reasoning transforms the hierarchy problem from a puzzle requiring physical explanation into a selection effect that reflects the requirements for observers to exist. The weak anthropic principle states that observed values of physical constants must be compatible with the existence of observers at some location and time in the universe. Since we are observers, any constants we measure must fall within ranges that permit the formation of stars, planets, atoms, and ultimately, biological complexity sufficient to support intelligence. The strong anthropic principle goes further, suggesting that the universe must have properties that allow observers to develop within it at some stage. This stronger version implies that the existence of observers is not accidental, but somehow required or inevitable, though the mechanisms by which this requirement might be implemented remain highly controversial. Dr. Brandon Carter, who originally formulated the anthropic principle, explained its application to physical constants. We shouldn't be surprised to find that fundamental constants have values that permit our existence, because universes with different values wouldn't contain observers capable of measuring those constants. The act of observation itself selects for anthropically favorable values. Gravity's weakness plays crucial roles in enabling anthropically favorable conditions through its effects on stellar evolution, planetary formation, and cosmic structure development. If gravity were significantly stronger, stars would burn through their nuclear fuel much more rapidly, potentially preventing the billions of years of stable energy output required for biological evolution. Stellar lifetime calculations reveal the anthropic sensitivity to gravitational strength. A star's lifetime scales approximately as ml, where m is mass and L is luminosity. Since luminosity depends strongly on mass through nuclear burning rates affected by gravitational compression, small changes in gravity's strength can dramatically affect how long stars shine. If gravity were 1,035 times stronger than electromagnetic force instead of 1,040 times weaker, typical stars would exhaust their hydrogen fuel in thousands or millions of years instead of billions, providing insufficient time for planetary formation, chemical evolution, and the development of complex life forms. Conversely, if gravity were much weaker than observed, matter would never have condensed into galaxies and stars in the first place. The delicate balance between gravitational attraction and cosmic expansion determines whether cosmic structure can form and persist over cosmological timescales. Nuclear synthesis in stellar cores depends on the competition between gravitational compression and electromagnetic repulsion between protons. The observed hierarchy allows stars to achieve the high temperatures and pressures needed for nuclear fusion while maintaining stable burning for billions of years. Planetary formation requires gravity to be strong enough to aggregate dust and rock into planets, but weak enough that electromagnetic forces can dominate on atomic and molecular scales. This balance enables the formation of solid planetary surfaces and complex chemical processes. The existence of stable atomic matter depends on electromagnetic forces overwhelming gravitational attraction between electrons and nuclei. If gravity were comparable to electromagnetic force at atomic scales, atoms would collapse gravitationally, rather than maintaining the quantum mechanical orbital structure that enables chemistry. Carbon and oxygen synthesis in stars involves nuclear resonances discovered by Fred Hoyle, who noted that slight changes in nuclear force strengths would prevent the formation of these elements essential for life. Similar anthropic constraints might apply to gravitational strength and its effects on stellar nucleosynthesis. The multiverse provides a natural framework for anthropic reasoning by suggesting that all possible combinations of physical constants are realized somewhere in an infinite ensemble of universes. Observers necessarily find themselves in regions compatible with their existence. String theory landscape offers a concrete realization of anthropic selection through its vast number of possible vacuum states, each with different force hierarchies and physical constants. Environmental selection could explain why we observe particular values without requiring fine-tuning of fundamental parameters. Eternal inflation naturally generates multiverse structures where different regions have different physical properties through stochastic processes during exponential expansion. Anthropic selection operating across this ensemble could explain observed force hierarchies as consequences of observational bias. The measure problem in multiverse theories asks how to assign probabilities to different observations when infinitely many of each type occur across the ensemble. Resolving this problem is crucial for making anthropic arguments quantitative and testable. Critics of anthropic reasoning argue that it is scientifically unsatisfactory because it doesn't provide predictive power or explanatory insight into why particular values are realized. They contend that anthropic arguments can explain almost anything after the fact without offering genuine understanding. The fine-tuning debate centers on whether the apparent precision required for anthropic conditions indicates design, multiverse selection, or unknown physical principles that constrain possible parameter values. Each interpretation has different implications for how we understand the relationship between physics and existence. Testable anthropic predictions might emerge from detailed analysis of which parameter ranges actually permit observer formation and how these ranges relate to fundamental physics. Some anthropic arguments make specific predictions about properties of dark matter, dark energy, or other cosmic components. The cosmological constant represents an even more extreme example of apparent anthropic fine-tuning, where the observed value seems to be precisely calibrated to allow galaxy formation while preventing premature cosmic acceleration that would disrupt structure development. Anthropic constraints on particle physics include requirements for stable protons, appropriate neutrino masses for Big Bang nucleosynthesis, and absence of exotic particles that could disrupt stellar or biological processes. These constraints might explain some features of the Standard Model. The dimensionality of space itself might be subject to anthropic selection, with 3 spatial dimensions being optimal for stable orbits, wave propagation, and other phenomena required for complex structures. Gravity behaves very differently in higher dimensional spaces. Anthropic reasoning about force hierarchies suggests that electromagnetic dominance over gravity at small scales might be necessary for stable chemistry, while gravity's ultimate dominance at large scales enables cosmic structure formation. The observed hierarchy might represent an optimal balance. Biological constraints on physical constants include requirements for liquid water, stable DNA, efficient metabolism, and other biochemical processes that depend on particular relationships between fundamental forces. These biological requirements might be more constraining than purely physical considerations. Information processing arguments suggest that consciousness and intelligence might require specific physical conditions that constrain force hierarchies. The ability to store and process information might depend on particular relationships between electromagnetic, quantum mechanical, and thermal effects. Alternative biochemistries based on different solvents or molecular structures might relax some anthropic constraints while imposing others, potentially changing the acceptable ranges for force hierarchies. Understanding the full space of possible life might affect anthropic predictions. The Fermi paradox, the apparent absence of detectable extraterrestrial intelligence, might relate to anthropic constraints if intelligence requires extremely specific conditions that are rarely satisfied even when basic life is possible. This could affect how we interpret force hierarchy requirements. Future observations of exoplanets, astrobiology, and cosmic evolution will provide tests of anthropic predictions by revealing how common or rare the conditions for complexity actually are. These observations might support or refute anthropic explanations for force hierarchies. Machine learning approaches to analyzing anthropic constraints might reveal previously unknown requirements for observer formation or identify which physical constants are most crucial for enabling complexity. These analyses could refine anthropic arguments about force hierarchies. The development of artificial intelligence and digital consciousness might provide new perspectives on anthropic reasoning by revealing whether intelligence requires biological substrates or can exist in different physical contexts with different force hierarchy requirements. Quantum mechanics might affect anthropic reasoning through the many worlds interpretation, where all possible outcomes occur in parallel branches. This could change how we think about observer selection and the meaning of anthropic constraints. Dr. Martin Rees reflects on anthropic approaches to force hierarchies. Whether you find anthropic reasoning compelling or not, it forces us to consider the deep question of why the universe seems so precisely calibrated for complexity. The weakness of gravity might be telling us something profound about the relationship between physical law and the possibility of observers. Anthropic reasoning about gravity's weakness transforms the hierarchy problem from a technical puzzle in fundamental physics into a profound question about the relationship between cosmic evolution, complexity, and consciousness, suggesting that the universe's structure might be intimately connected to the possibility of observation. Understanding anthropic perspectives on force hierarchies reveals how the existence of observers might constrain or explain the fundamental constants we observe, demonstrating the subtle but potentially crucial connections between physics, cosmology, and the nature of existence itself.